Hello everyone. Today we will discuss using this Laplace transform we discussed in the previous three videos to solve differential equation or what we call the Integro-differential equation. So we'll move again quickly on the useful properties to solve this differential equation. And for your information, this is one of the most important application to use this Laplace transform. So let's move forward and see how you use these properties. So from Laplace transform, what we discussed before, we have any function f of t, and Laplace of this function, it's nothing but another function in S domain, which is f of s. For example, if we have instead of f, it's called y of t, so it will have this Laplace transform y of s. If we have the derivative, from the properties, if we have derivative in the time domain, it will be multiplication by s in the s domain, and there is another term here added to this formula to be y of 0, and this y of 0, it's nothing but the value of y of t at t equal to 0. If we have the second derivative, this one is has Laplace transform with s squared multiplied by y of s multiplied by the first derivative by the function at at t equals 0 minus the derivative of this function y dash of t at t equals 0. So again, this is the value of y dash of t, this at t equals 0. If we have the third derivative, this term will have Laplace transform s cubed multiplied by y of s minus s squared y of 0 and minus s y dash of 0 minus y double dash of 0. So generally speaking, if we have the nth derivative, this will have Laplace transform in the form of s of the same power multiplied by y of s minus s minus the power n minus 1, so minus 1 of this power to the power of s multiplied by the value of y of t at t equals 0, and this would be with the same sequence as previously discussed in the last two rows. And the last term will be the nth minus 1 derivative at t equals 0. This will be our constant. So this will be very valuable information to transform the y of t and its derivative to the y of s domain. As we can notice here, all these terms, just we have some scalar multiplied by y of s instead of dealing with these derivatives here. So this for sure would be very helpful in using these all formulas to solve a differential equation. One also very useful thing, if we have the integral equation, so if we have some integrals on the form that we already knew before, if we have integration from 0 to t, any function y of tau d tau, this will have Laplace transform in the form that f, or right now, make it the right thing, it will be the form of this y of s divided by s. If we have second integral, so two integrations, this it means it will be divided by s squared. This for sure, it will be y of s. So this way. Sorry for that. So here it will be the same thing. If we have derivative, we'll have the other side multiplication. If we have integration, it will be the other side division by s. Using these properties, we can solve differential equation. How we can solve these differential equation? Let's see here. If we need to solve any differential equation, so it means we have terms of, like, for example, y triple dash of t, and we have another terms like y double dash, and some other terms y dash of t, and without derivatives, it's y of t, and the other side, on the right hand side, some function of t. Something to notice at the beginning, Laplace transform can be applied just for solving linear differential equation. What do you mean again by this linear differential equation? It means all terms of y of t and its derivatives will be to the power of 1. So it means this y triple dash, it will have some coefficient here, a3 for example, this some coefficient, a2, here is another coefficient a1, here is another coefficient a0, and equal some function of t or constant. But again, if we find anything in the terms of y triple dash squared, this is nonlinear. So this Laplace transform here is not applicable. If we have some other thing in the form of y dash multiplied by y, this term also makes the equation nonlinear. If we have terms like y squared, root squared, y, all these terms are not applicable to be a linear differential equation. So first, if we have this linear differential equation, our steps will be straightforward. So to solve this differential equation, first, transform the differential equation into algebraic one. So it means these all derivatives will be transformed using Laplace transform to the s power n. And then the second step, which is the main step here, simplify. So simplify y of s in one side equal another side here as a function of s. This function of s, again, it's required to solve the differential equation. To solve it, it means we need to get y of t. So y of t, it's nothing but Laplace inverse of this y of s we got here. So again, this transformation, we will be using the properties we discussed previously in videos number 1 and 2, and then we will end up getting Laplace inverse, which we need to use what we called how to find the inverse of Laplace transform, which is in video number 3. So moving together between the three steps, you will end up with this y of t, which is here the solution of this differential equation. So this is the solution of the differential equation. So let's see some example solving this one. So it's required to solve the following differential equations. First, we have a differential equation. This differential equation, it's y dash plus, so it's here y dash plus 4y equal e power minus 4t, and given the initial condition of y of 0 equal to. So trying to solve this one here. So first step again, doing this Laplace transform. It means the first term will be s y of s minus y of 0 plus 4y of s. So these first two terms corresponding to the y dash, and then this 4y, it will be 4y but in s domain, and don't forget this exponential here, it will be nothing but in the transformation of the table s plus 4. Again, we have this y of 0 here given, so we have this value equal to 2. So substituting this equal to 2 and take y of s common, so y of s will be multiplied by s plus 4, and this 2 will be in the opposite side to equal 2 plus 1 over s plus 4. So it means this y of s This is our second step was for the simplification. It will be 2 over s plus 4 plus 1 over s plus 4 squared. Okay, so the last step. What's y of t? Y of t, it's Laplace inverse of this y of s, which is 2. The first term is the exponential. It's very straightforward from the table. And the last term, this one is shifting properties for s squared. So it's e power minus 4t Laplace inverse of 1 over s squared. So this means y of t will be 2 e power minus 4t plus e power minus 4t multiplied by t. And this is your y of t. Sample check here. We have y of 0 given equal to 2. So let's substitute. So y of 0 will be 2 e power 0 plus 0. So e power 0 equal to 1. So if that's 1 equal to 2. So it means it's the correct answer. So again here, moving through this whole example, we have y dash plus 4y equal e power minus 4t. We got Laplace transform of the equation on the left-hand side. It will be s y of s minus y of 0 plus 4y of s, and the exponential is 1 over s plus 4. And then y of s for the simplification will end up as 2 over s plus 4 plus 1 over s plus 4 squared. The first term, it has Laplace inverse from the table, it's exponential. The other term has this shifting property first can taken out. So it will be e power minus 4t, and the remainder term at 1 over s squared will have Laplace inverse t. So this our solution of this differential equation, which y of t equal to e power minus 4t plus t e power minus 4t. So trying solving another example here. Let's move forward. So let's see here if we have example number 2. We have y double dash minus 6 y dash plus 13y, this equation equal to 0, but given y of 0 as 0 and y dash at t equal to 0 given as minus 3. So solving this equation again, the first step to get Laplace transform. So the first term is s squared y of s minus sy of 0 minus y dash of 0. And the second term will be minus 6 sy of s minus y of 0. The last term was the 13 multiplied by y of s, and all of these terms equal to 0. We have given the values for y of 0 and y dash of 0. Y of 0 is equal to 0, so these both terms are zeros. Y dash of 0 is equal minus 3. So here we can take common y of s multiplied by s squared minus 6s plus 13. And on the other side, this plus 3 will be here minus 3. So again, y of s will be equal minus 3 over s squared minus 6s plus 13. For the simplification, we can't do here this partial fraction. There is no factorization can be done. So we'll do the complete square. So this will be s minus 3, which is half the 6 here, squared. And then here this is plus 9, so plus 13 needs this 9 to be 13. It needs another 4. So this term here, it has the shifting, which is e power 3t. And then we have another term, which is 3 over s squared plus 4, which is related to sine or cosine, but the numerator is a constant, so this is the sine. So again, y of t will be Laplace inverse of this term, which is minus 3 over s minus 3 squared plus 4. So this will be equal minus 3 e power 3t, and we have the other term, we already end up this out. So 1 over s squared plus 4, it's sine 2t, and it should have this 2 in the numerator, so I will divide by this 2, and then this will be our y of t. So again, we have a simple check for this value if whether it's correct or not. So just do the substitution. We need to go through y of 0 and y dash of 0. Y of 0 here, if we are substituting with 0, we have this sine 0, so it will end up e power 0 sine 0. Sine 0 is 0, so this term is 0. Y dash of 0, it will be here we have this constant minus 3 over 2, and this is the product of two functions. So the first the derivative of the second, and the second by the derivative of the first. So it will be e power 3t, 2 cosine 2t, plus 3 e power 3t, and sine 2t. All of these terms at t equal to 0, so this term it will be 0, this it will be 1, this will be 1, and it will end up minus 3 over 2 multiplied by 2, it will be minus 3. So y dash of 0 is minus 3. Comparing these values together here, so this value and this value, it's the same as y dash of t at t equals 0 and y of t at t equals 0. So it means this most probably the correct answer for this question. So let's see another example here. So let's see this example here. We have this y double dash minus 2y dash plus y equal e power t, and given y of 0 equal to 0 and y dash of 0 equal plus 5. So moving through the previous examples here, it will be the same straightforward transformation. So y dash of s here, y double dash, it will be s squared multiplied by y of s minus s y of 0 minus y dash of 0 minus 2. Y dash will be s y of s minus y of 0, and then y of s will be y of t, it will be y of s, and e bar t, it will be 1 over s minus 1. We have again given the values for y of 0, this one 0, this one 0, y dash of 0 equal to 5. So keep this substitution, I will take this y of s common. So this will be s squared minus 2s plus 1. And then when the other side, this minus 5 will go, the other side will be 5. And we have 1 over s minus 1. So again, this y of s will be 5 over this s, and this can be simplified as s minus 1 all squared. And this one here would be s minus 1 all cubed. So here, it means y of t, well, it's Laplace inverse of this y of s. It means Laplace inverse of the first one, s minus 1 squared, and the other one, which is 1 over s minus 1 cubed. So y of t will be 5. We can take this shift out, which is made s to be s minus 1. So we can get this minus 1 out. It will be e power t. And then we'll have this 1 over s squared. And again, e power t, Laplace inverse of 1 over s cubed. So here this will be 5 e power t, 1 over s squared came from t, and the other term, which is 1 over s cubed, came from t squared over 2 factorial, which is 2. So here this is y of t. Again, as we did multiple times, simple check, take y of 0, by simple substitution, it will be 0. And if we got the derivative at t equal to 0, so just simple substitution here, you will end up with this 5. So this means this is the solution of this differential equation, and this is the y that can solve this derivatives to have this left-hand side and right-hand side of the equation number 3 equal to each other. So we have right now our example number 4. We have here the equation y double dash plus 9y equal to cosine 3t. Given y of 0 equal to 2 and y dash of 0 equal to 5. Again, repeating every single step we did before. So this will be s square y of s minus s y of 0 minus y dash of 0 plus 9 multiplied by y of s equal cosine 3t, which is s over s squared plus 9. We have the values given for this y of 0 equal to 2, y dash of 0 equal to 5. So going further by simplifying those terms here, so y of s will be multiplied by s squared plus 9. On the other side, we will have this 2s plus 5. And here we have the other term s over s squared plus 9. So again, we will have this y of s more simplified. It will be 2s over s squared plus 9 plus 5 over s squared plus 9 plus s over s squared plus 9 all squared. We need to get Laplace inverse for each one, so y of t could be simply written as the first term is 2 cosine 3t. The second term is 5, and this is the sine 3t, but it has to be 3 in the numerator, so I will divide by this 3. The other term discussed before, if we need to get Laplace inverse for this s over s squared plus 9 all squared, we had some few steps like this one. If this is our f of s, we have this term s over s squared plus 9 or plus something squared. We can do what's called the integration from s to infinity, and this is u over u squared plus 9 squared u. And then this integration will end up with minus 1 over u squared plus 9. And we have this derivative here, it has to be 2, so I will divide by 2. And substitute with s and infinity. Substituting with this one here, by infinity it will be 0. The other one will be 1 over 2 s squared plus 9. Moving forward, Laplace inverse of this integration, it was the f of t divided by t. And Laplace inverse from the right hand side, this is the sine 3t divided by 3, and we have this half scalar constant outside. So it means f of t cross multiplication. This means our final solution will be 2 cosine 3t plus 5 over 3 sine 3t plus this term here multiplied by t. It will be t over 6 sine 3t. And this is our solution. Sample check as previously discussed, y of 0. At t equal to 0, both sine terms will be zeros. It will end up with the cosine term will equal to 2, so that's correct. The other thing is y dash at t equal to 0. The cosine will be sine, so this will be 0. The sine term will be cosine, and you will have this 5 outside, so you'll end up with 5. And the other term was t multiplied by sine. You will have t cosine plus sine. Both terms at t equal to 0, so this will be done 0. Yeah, and that's correct. So that's the solution of this differential equation. So again, let's see another type of differential equation, or what we call Integral-differential equation, or even integral equation. So it doesn't matter. We have this, let's see, this function f of t, which is still unknown, and we have integration from 0 to t, and then f of tau d tau is still the integration of this function, which is still unknown function, equal to 1. And what's required is how to find the value, or find the value of this f of t. So again, using Laplace transform properties, we can transform this equation into algebraic one. So we have, instead of f of t, it will be f of s. And then this integration will be f of s divided by s. And then this one, don't forget, it's 1 over s. So taking this f of s common, it will end up with 1 plus 1 over s equal 1 over s. And then for simplification, make this common denominator. So this will be s plus 1, and here 1 over s. So this equals 3. So f of s at the end will be this 1 over s plus 1. Like this s and this s, both denominator cancel each other. So it means this f of t, right now it will be e power minus t. What this means? This means if we are taking this f of t here and substituting with this function, and again doing the integral from 0 to t for this exponential, and adding both together, this will end up with 1. So just check to confirm the correctness of this solution. So we have e power minus t, and you have integration from 0 to t, e power minus tau d tau, and we need to check the value of this whole left-hand side. So this will be e power minus t. The integration will be e power minus tau, and this divided by minus 1, substituting by 0 and t. This will be e power minus t, and then will be plus e power 0 minus e power minus t. This cancel each other. E power 0 will be 1, and then this whole left-hand side will be equal to 1. And that's what we're already seeking. So that's what means we need to solve this equation. Again, this is not a differential equation as previously discussed once, but this one is integral equation. So let's see another example for this integral and differential equation. So here we have this example number 7. We need to solve the equation, which is y dash of t equal to 1 minus sine t. This is still differential equation. And then the new term, integration from 0 to t, this y of tau d tau. And given, according to this differential equation, we have the initial condition, which is y0 equal to 0. So here we have this differential part, and we have this integral part. So this is what called both together. This will be the Integrodifferential equation. So how to solve these ones? There's nothing new. Still the same steps. So using Laplace transform, this y dash will be s y of s minus y of 0. And then we have this 1 will be 1 over s. Sine will be 1 over s squared plus 1. The integral will be what inside this integral, which is y of s, and the integral itself, it will be division by s. We have the value of this y of 0 given it's 0. So again, we need to simplify. It's the same steps, nothing here to be concerned new for us. So this y of s, it will have this s, and I'll move this other term to the other side, so it will again have this 1 over s equal 1 over s minus 1 over s squared plus 1. So more simplification, so this y of s, make it in 2 steps. It will have this s squared plus 1 divided by s we'll have here 1 over s minus 1 over s squared plus 1. So again, this will end up with this y of s will be equal 1 over s squared plus 1. This is the first term. And the second term, which is s over s squared plus 1 squared. This is from the table, so that is straightforward. We did this multiple times till now, so this will be using the integration. So I need to do some integration. And then I will end up with something divided by t, and then multiply by t. So this will came from t sine t, and the 2 is not here, so it will be divided by t. And this from the table, it's sine t. So it means this y of t at the end, it will be sine t minus t sine t divided 2. And again, if we have a function like this one, simple check, at the value of y of 0, again, by substitution, both sine 0 will be 0. So this will give you preliminary check that we are moving in the right direction. So let's see something more